Very good evening to one and all. And welcome back to Patel sponsored 6 days online FDP in the title of Next Generation Green Energy Powered Electric Vehicle and Renewable Energy Integration using Solar Microgrids. We successfully completed 5 days and we are entered into 6 days. In the 6 days, we are entered into second session in the title of Modeling of Lithium-Ion Battery for EV Vehicle Application in the expert title of Bansal Bhairava. Sir, I is here, Assistant Professor, School of University, Bangalore. With a notable academic and a profound impact in the field of electrical engineering and battery modeling of EV vehicles. He has a degree from NIT Surathkal in 2016 and PhD from MNIT Jaipur 2020. Dr. Bhairava has published 61 Scopus Index papers and received multiple awards, including the Best Researcher Award on Teachers' Day 2024 and 2 IEEE Best Paper Awards and 1 Best Poster Award in DST Industry Academia Conclave. A recognized expert in battery modeling, he has secured 5 KS CST project grants, 15 various institutions is recognized HTMX of on Scopus and Google Scholar. He having 10 published Indian patents. Dr. Bensalal Bhairava followed by 15,500 plus performance on LinkedIn. Now I hand over the sessions to Dr. Bhairava sir. Please take the session, sir.
Sir, thank you very much for introducing myself. So first of all, I would like to thanks to Holy Mary Institute of Technology
I
for
think
inviting
your
me.
voice will be less, sir. If you don't mind, please
Hello.
increase
Yes.
the volume, sir.
So I would like to thanks to Holy Mary Institute of Technology for inviting me to deliver the session on
Now
battery
okay, sir.
modeling.
Now okay.
So I will share my screen. Please confirm once it will be visible to all. So I hope my slide is visible. It's visible to?
Yes, sir, visible.
Yes. Thank you for confirming. So very good afternoon all. In today's session, we are discussing about modeling and lithium-ion battery for electric vehicle applications, like how to model the batteries. So we are electrical people. If we will see the battery, then what we'll do? We will connect the voltmeter in the parallel, and we can measure the voltage, like how much voltage it is there. Okay. And if you want to measure the current, when we will insert one ammeter in the series, we can measure the how much current is flowing across this closed loops. Okay, but problem is like how to model that battery, because if you'll see, and nowadays so many vehicles are getting the fire. People are having the afraid to buy the electric vehicles because of one reason, that is EV. Because we don't know, there are uncertainties are there, like maybe battery may get the fire. Okay, so we are experiencing this issue in nowadays, and there are many examples, like in the last 6 months ago in JP Nagar, one EV caught the fire, and Yokinawa. There are so many applications. So why this is happening? Because of improper modeling of the battery. We should not like developer or industrial person, they should not develop the battery without proper testing and validation. Okay, so here our main role is to develop the battery model that can predict the battery behavior under wide variety of conditions. So today we will discuss in the depth, and then we will also do some hands-on. If your MATLAB is on, then I will tell how to develop the battery model. So here is the outline. We will discuss about the batteries, basics about the batteries, battery configuration, cell voltage for various types of batteries, roadmap for battery energy storage, CCCV charging. This is important here because if in normal charging station they are following this CCCV charging protocol. Then battery capacity, C rates, battery state of charge, battery state of health, various types of battery modeling method. Then finally we will go for the cell level modeling. That is our main task of today's session. Because if battery bank, let me disconnect this. If you'll see the battery bank, there will be so many batteries are connected in the series and parallel configuration. So we have to develop the cell. Yeah, so here we will do step by step process, and we will develop one cell model that that will be the main outcomes of this today's session. Okay, so this here is the introduction about the batteries. Many of are aware about the batteries, like what is the battery. We know very well. Battery is an electrochemical device that store the charges, and when we want that charge, we can take it. Okay, take it back. So battery is not generating the electricity. Battery is just energy storage device, and we, as per the law, like energy conservation law, where energy can't be destroyed and can't be created, right? So battery is not that, battery is just energy storage. We are storing the energy and we are taking energy back. Okay? So we have to understand the battery, like what is the battery. Okay, so if you'll see battery having the four important parameters: anode, cathode, electrolyte, and separator. Okay, so here I want to request the participants, if my voice is not audible properly, you can raise the query, because I have connected to the Wi-Fi. If my Wi-Fi is disconnected, then it should not be an issue for, means you can confirm or you can call. So we are talking about the battery. Battery having four parameters: anode, cathode, electrolyte, and separator. Okay, so firstly I will discuss simply in the normal language, like what is the battery, what is the anode, what is the cathode, then what is electrolyte, and what is the separator. These four things will be there in all types of the battery. Okay, these are the main component of the battery. So as per the definition, the electrode where oxidation is happening during the discharge condition. So in this condition, electron will flow from anode to external circuit, but in closed loop path. Then again cathode. So cathode is electrode where reduction occurs during discharge, and electron returns to the cathode through the external circuit, right? Then electrolyte is a substance and material that may be the lipid or gel. That is some solution that allow the ions to move between anode and cathode. It serves as a medium for flow of electric charge, right? So last one important parameters of the battery, that is separator. So this is just a physical barrier that prevents the direct contact between anode and cathode, and allowing ions to move while keeping the electrodes from touching. Okay, so this is the just normal definition of the battery that as per the book definition. Okay, we will understand in different perception and different analogy, like what is the battery. Battery, as per me, battery is nothing but case, CAAC. Okay, battery is nothing but a case. As I told, like there are so many cases is happening because we are catching the fire. Okay, so what is battery? Battery is nothing but case. So what is C? C is cathode, A is anode, S is separator, and E is electrolyte. Okay, so battery is nothing but a case. Again, okay, we can understand this in different things, like we are the teachers, so we having the uh, boys in the classroom, like we can treat a cathode is a boy and anode is a girl, or anode is a girl and cathode is a boy. So, and electrolyte is the money. Okay, so if there is no money, then they can't come together. And separator are the teacher, so they will separate them. Okay, because they should not come together. So so that's why so many cases is happening in the classrooms also. So we can understand in that analogy, don't mind that. But as per me, what is that? Battery is nothing but a case. CAAC, that is cathode, anode, separator, and electrolyte. So there are n number of applications is there for the battery. We will go from basics to, we will go to high level modeling of the battery. Okay, so firstly we will understand the basic concept of the battery. So there are battery applications is divided in three parts majorly. That is a growing market and gradually saturated market. So we are using the smartphones, laptops, tablets, power tools, and personal care. So here, this market is gradually saturated. Means earlier we will be having 5000 mAh battery. Now 6000 mAh also is there. So what is that mAh? Means that battery can deliver the 6 ampere current for 1 hour, right? So this market is gradually saturated. And again, we can understand if even 2 years back, or okay, we will not say 3 years back. 3 years back, if we were purchasing the mobiles, that time we can see the batteries, like we can open that cover and we can see the battery inside the mobile, right? But nowadays it is not happening. Battery is fully sealed, and we can't open that battery and we can't see the battery. Why? Because of safety reason. Okay, because of safety reason, and we are aware about that. Like if temperature is increasing inside the battery, and it may blast, right? So if they are covering it properly, if blast is also happening, means minimum damage will be there. Okay, so that is the main reason for covering the batteries. Even no one can see the battery, like which what battery is there inside the our mobile, because this is fully covered. So we can say this market is gradually saturated. Okay, smartphones, in the laptop, in the tablet. But in other hand, this transportation and this grid energy storage, grid energy and industry. So this market is growing market. Like there are so many, means research is happening, but still some drawbacks are there, and more research is required in this market, in transportation and grid energy storage based. Okay. So here is the applications, like in the grid energy, if you're talking, then portable energy storage. This is portable storage, means this is nothing but battery only. Okay, so we can this is just like the carry bag. So battery is there. We can shift from one place to another place, and we can take the current from these batteries. Okay. In the renewable energy, like we are using the solar power plant. So again, solar power plant is two types of. First one is standalone solar power plant, and second one is grid connected power plant. So grid connected is directly connected to grid, but standalone power plant, if we are generating the solar energy, okay, like again solar energy is depend on the solar irradiance, how much irradiance is there, like watt per meter square, and you know very well, like 1000 watt per meter square is the highest solar irradiance in the earth surface, right? It is more in the space, but in earth we are getting 1000 watt per meter square. So this solar panel will generate the power as per this, and solar irradiance. So if 1000 watt per meter square means it will generate more power. So whatever power we are generating through this solar panel, where we have to store, because it will generate the DC power, right? So we have to store this DC into somewhere, because in night time, as I told, we are talking about standalone solar power plant. Standalone solar power plant. So in night time there is no sun. So if there is no sun, then we need the energy still. So we have to store this DC energy in some battery bank. Okay. So later we can use, right? So this is growing market, and if you'll see the solar power station, solar power plant that is standalone, there is still you can found that lead acid batteries. So if we can also replace lead acid battery with the lithium ion, but again cost will come into the picture, right? Cost is more. So that's why we can say this is growing market. Okay, in transportation sector, I want to mention here, like those any faculty and research scholar having that expertise in the battery and electric vehicle and the robotics, they having the bright future ahead. Okay, so this is growing market, and more research had to be happen there. Okay, so we can say even India also there are so many EV cars is there. In the Bengaluru, you can find, you can see every minutes you can see more than 10 EVs in the road. Okay, so EV market is also growing nowadays. So these are the examples: automobile, forklifts, buses, and cars. Right. Okay. So these were the applications. I should not keep more time there. But next right side you can see the one graph that is Ragon chart. So we should understand like what is the Ragon chart. Ragon chart is nothing but just the comparison, or just the comparison of the volumetric energy density versus gravimetric energy density. So what is gravimetric energy density? Gravimetric energy density, that is unit is watt hour per kg. Okay, watt hour per kg, and here volumetric energy density is watt hour per liter. Okay, so we will understand this. Like what is the watt hour per kg means, in 1 kilogram lithium, in 1 kilogram lithium ion material, how much energy we can store, because you know very well what is the unit for the energy. Unit for the energy is joule, but in electrical terms we can measure the energy in watt into hour, like how much power we can deliver for 1 hour. That is what, that is energy, right? So in 1 kilogram of lithium ion or any type of chemical property, how much energy we can store, that is called as a gravimetric energy density. So here you can see lead acid battery, nickel cadmium battery, nickel metal hydride battery, and lithium ion batteries. So comparing to all, here if you will draw this line here and this time here, this line here. Okay, so that is 220, you can consider, means 220 watt hour per kg. In 1 kilogram lithium ion we can store 220 watt power, and we can deliver it for 1 hour, we can release. That is the gravimetric energy density. Similarly, for the volumetric energy density, like in 1 liter of iron, how much chemical, how much energy we can store. Okay, so that is volumetric energy density. So if we will compare all type of the chemicals like cathode materials like lead acid, nickel metal nickel cadmium, comparing to all, lithium ion having the more energy density versus high volumetric energy density versus high gravimetric energy density. So we are focusing towards the lithium ion, because there are also more expectations there for the lithium ion. Why only lithium ion? This is about regarding the energy density. Like again, energy density is divided in two parts: gravimetric and volumetric. So energy density of the lithium ion is more comparing to other type of the batteries, right? Then again, lithium ion chemistry is divided in 6 parts. Lithium ion having the 6 type of chemical properties in the cathode material, that we will discuss later. So there are so many applications is there as per that this energy density, because we want more and more energy. Okay, so when we are developing the battery, and we are modeling the battery, several factors will affect the battery models. Okay, so what is that? First of all, ambient temperature. Okay, then I square R. So I is the R is the your internal resistance and I is the current. So like you can say that is self discharging. Okay, comparing to other things, other like super capacitor, and so battery self discharge is less. Then C rating, aging. Again, aging is divided into part, that is calendar aging and cyclic aging. Cyclic aging and calendar aging. So cyclic aging means we are charging the battery every day. We are charging and discharging a battery. So we must understand. We should know this. Like, what is the one cycle? What do you mean by the one cycle? So one cycle is nothing but charging the battery. Like here you are charging. This is the y-axis. This is the x-axis. You are charging the battery. Okay. So and this y-axis is the SOC, state of charge. State of charge is nothing but SOC only. So here maximum SOC we have to consider, like maximum SOC is 100%. 100% SOC means fully charged condition. So here we are charging and it is taking two hours. Okay. So here within 2 hours of normal charging, it taken 2 hours. Then again, this is the discharging time. Okay. So here discharging time is 10 hours. Okay. So from year to year, this is called one cycle. One cycle. Okay. From charging and discharging, right? So if we are using the battery and we are charging and discharging the battery, right? So means we have utilized one cycle of the battery. We have utilized one cycle. So now, how many days are there in 1 year? In 1 year, there will be 365 days, right? So means what? We have utilized 365 cycles in a year. Okay, but all types of the battery having their fixed cycle life, fixed cycle life. Life cycle, you can say. So comparing to other battery, like we can assume this lithium ion battery having 2000 cycles. 2000 cycles, you can Google it. 2000 cycles means total number of cycles are 2000, and in 1 year how much cycles we used? 365. So we can calculate the age of this battery, right? 2000 divided by 365. So it will be the life of, like, whether it this battery can sustain for 3 years or 4 years. So this cycles depends on the manufacturer of that batteries. They will tell like how many cycles they have for this particular battery. Okay, so these are the factors that affecting the EV battery performance. Then next side is battery modeling challenge for electric vehicle. If we are developing the battery model, there are several factors that affect the battery modeling. Okay, so first one is proper sizing of storage. Okay, proper size. If you are aware about the electric vehicle, Tesla Model S, and there are so many advanced model came. They having the 100 watt hour. Okay, so if you are buying the EV, you are going to purchase EV, you will check? You will check the battery capacity, battery bank capacity. Like if you are buying some motorcycle there or any Activa, in Activa you will see like maximum 4 liter tank is there. Means what? You can fill the 4 liter petrol, and with 4 liter petrol, if it is giving the 60 kilometer average, so 60 into 4, you can travel with 240 kilometer in one single water. Say if you filled the tank one time, just this is the assumption, but you try. I'm trying to relate this thing to the battery bank. So we are talking about some gasoline powered IC engine based vehicle that are having the petrol capacity, tank capacity 4 liter. Okay, so if it is giving mileage of 60 kilometer, it will not give, but I am just taking assumption. So we can travel to 240. Similarly, for the EV, they will give the range of the EV. Like in one single charge, how much kilometer you can travel. Okay, so single charge means 100% SOC. Okay, so in 100% SOC, how much kilometer you can travel, right? So initially it will be the 100%. Like okay, so when you are traveling, this is the range. Okay, so they will give the, like it can travel the 500 kilometer, like Tesla Model S, that is a 1000 kilowatt hour capacity. So they told like 500 miles you can travel as per the Tesla. But we are talking about this sizing of the battery storage. So if in single charge, like how much distance you can travel. So when you are travel, when distance will increase, your charge will decrease, right? So it will reach to the 20%. And again, I am telling you, you should not discharge your battery below the 20%. Okay. So proper sizing of the storage is required, and what is the capacity of the, how to rate or how to measure the battery bank capacity. So unit of the battery bank capacity is kilowatt hour. Okay, kilowatt hour. Like if EV Mahindra is there, or any some all any EV company is there, then they should have the capacity. Like I will talk like some EV Mahindra is there, so that is 40 kilowatt hour. 40 kilowatt hour capacity means, what do you mean by the 40 kilowatt hour? Means that battery bank can deliver the 40 kilowatt power, 40 kilowatt of power for 1 hour. Here 1 is mentioned, 40 kilowatt into 1. We can multiply with 1, nothing will happen. So 40 kilowatt hour means it can give the maximum 40 kilowatt for 1 hour. Okay, but we are using the what are the components? Main component is the EV motor. So once we will give the supply to the motor, it will rotate. Okay, so that motor having like 10 HP. 10 HP is more, but okay, I am taking as an example of 10 HP. So okay, 5 HP. So 1 HP equals to how much? 1 horsepower equals to how much watt? If anyone can tell me, then it will be the great thing. So I can see your activeness towards this session. 1 HP equals to how much watt?
735 watt. 735.
9. That is okay. You are nearby that only, but
746.
correct. 746 watt. Okay. So 746 watt. And what assumption we have taken? 40 kilowatt hour. 40 kilowatt hour means as I told, 40 kilowatt hour. So if it is 4 HP motor in the EV, means 5 into 746 watt. Okay, that much power only it can consume. So we can calculate the time. So 40 kilowatt, 40 into 10 to the power 3 into hour. That is okay, 60 minutes. Okay, or we can type here 1 hour. Okay, so divide by 5 into 746. Okay, so here we can calculate like how much hour we can travel if we are using the 5 HP watt motor. Okay. So proper sizing, but again, what is happening, there are so many components is there in the EV, and manufacturer will tell like in one single charge it will you can travel 500 kilometer. Okay, so again after 500 kilometer we have to charge our EV. So proper sizing is major concern here. Some EV using the 40 kilowatt hour capacity of the battery bank, some EV having the 60 kilowatt hour. So that is not fixed, this is varying. Okay, so this proper sizing of the storage is one challenge. Parameter identification. So what is that parameter? What type of parameter we are talking about? So if we have the electric vehicle, okay. So in the electric vehicle, we have the battery bank. So in battery bank again, how to develop that battery bank means batteries. First of all, we should talk about battery. So battery is nothing but combination of cells. Okay, if you have checked some one lead acid battery, once you will remove that upper portion, you can see so many lead acid plates are connected. Okay, that is cell. That is cell. So if 6 cell is connected, then what? 6 into 2 means 12 volt. Okay. So battery is nothing but combination of cell. Then again, this battery, once we will connect the so many battery, then it will be the battery assembly. Then again, if we will connect the so many battery assembly, then we will create the battery pack. Then again, so many battery pack will create the battery bank. Like, so cell is the smallest unit. Okay, so we need to identify the cell parameters, like how what type of parameters we have to identify, we have to estimate. Okay, 1 second. I will turn on my camera. So in the electric vehicle or in the EV cells, we need to check the battery capacity. We need to identify the battery capacity. So battery capacity, if you are going to buy some battery, then you will tell like how much AH you want. Okay, so that is rating of the battery is the voltage and AH capacity. How much voltage and ampere hour, that is battery capacity. Then parameters like if that battery is developed based on the ECM, that is equivalent circuit model, or electrochemical based model. There are again different types of battery models is there. So in current, as per the research I am telling, like there are 4 types of battery models are available. So one is electrochemical model, and another is empirical model, another is data driven model, and last one is electrical equivalent circuit model. Electrical equivalent circuit model. And we know this because if we are not from the chemistry background, but we can understand the battery. Like battery, what is main concern? Main concern is SOC and temperature. Okay, so if you are using some EV and you are in the Rajasthan, there is 45-degree temperature is there. So that time, what behavior of the battery will be like? In battery, what we can do, either we can take the current from the battery, or we can charge the battery through the current only. Okay, so when we are charging and discharging the battery, what parameter will affect? One, voltage behavior will vary. Voltage will vary. Okay, so we need to identify the, if we are from the electrical background, so we can understand this electrical equivalent circuit model. Like based on the R and C element, we can design and develop the battery model. Okay, so comparing to electrical all type of methods, I will recommend the ECM model, because this ECM model is in the ECM model, the battery voltage, terminal voltage, is the function of R component, C component, temperature, and SOC. Okay, RC element and temperature and SOC. So easily we can control this R and C and temperature and SOC. Premature failure prediction for the state level architecture, state estimation under real time condition. State estimation means SOH and SOC and SOH. SOC is state of charge, SOH is state of health. So this is the challenge, like in the real time, how we can estimate this state of charge. Lifetime improvement other than the rigorous driving conditions. So if we are using the AV and our, if you are traveling with the EV and you want to go with the high speed, so yeah, if you want to go with the high speed, you will extract more current from where you will extract from the battery bank. Okay, and that extracted current will go to the motor. So motor will run fast with a more RPM. Okay, right. So drive condition will be changed. If you are a normal person, you will go slowly, aram se, and battery will not be affected more. But if you are going to some Nandi hills, there you are going to upwards direction. Okay, some slope is there. Then it will be a burden on the battery. Okay, because okay, you can ride on this because of this motor. Okay, but from where you will take the current? You will take the current from the battery, right? So battery will discharge early. So there will be different drive conditions. Then stake level health assessment. This is also major concern. Stake level health assessment, because in the electric vehicle, as I told, electrical vehicle battery bank is combination of various cells. Combination of the various cells. In the EV battery bank, there will be 1,000 cells, maybe more than 1,000, right? So that is a combination of various type of cell that is connected in series and parallel configuration. That also we will discuss what is the series and parallel configuration. So this, if there are so many cells are connected, okay, and one faulty battery is there. One faulty battery is there. So that faulty battery will create the problem. If blast is happened, so because of that blast, other battery also will be affected. Okay, so and that cell was there inside the stack. As I told, there will be different stack, and we will do the stack level modeling also if time permit. So this stack level health assessment is also the major concern in the battery. Okay. So as I was talking about the EV battery bank, there will be more than 1,000 cells. Okay, that is connected in a series and parallel configuration. So here I will take one example. I need your attention here. This is lithium ion cell. Okay, we will consider this is the lithium ion cell. Okay, and we know if you are buying the if you have the lithium ion battery, so there will be the voltage rating, there will be the capacity, that is in AH. Okay, so these two parameters is important in the battery, voltage and AH capacity. So this is all the same cells having the same rating. So I will consider this providing the 3.8 volt, okay, and 10 AH capacity. 10 AH, okay. This cell. So all cells having the same capacity. So anyone can tell me how much current will flow across this closed circuit? This bulb is there. How much current it will flow? If you are electrical people, definitely you will answer this. Anyone can respond? You can raise your query. Definitely, I will try to solve. So how much current will flow here? As I told, there are 3 cells are connected in the series. Okay, and each cell having 3.8 volt and 10 Ah capacity. So how much current will flow across this circuit? You can join this session with the interaction. So we know very well, we are the electrical people, and we know current always same in the series, right?
10 each.
Correct. Current always same in the series. So 10 ampere, 10 ampere, 10 ampere. Here we will get only the 10 ampere. Okay, 10 ampere current will flow. We will develop the battery bank based on this calculation. But firstly, we should understand that concept of the battery. Because there are so many cells will be connected in the series and parallel configuration. As I told previously, like we have the one battery bank that having the 40 kilowatt hour capacity. So how to build this 40 kilowatt hour? Because there will not be one single battery. There are 1,000 cells are connected in. So based on the combination and configuration of that cells, we will develop this 40 kilowatt hour battery bank capacity, right? So this type of cells only will be there. Like here, this is the example of 18650R cell. Okay. Again, I will tell what is that 18650R. So these cells are connected in series. So how much current it is flowing? 10 ampere, because current is same in the series. But voltage will be 8. Here, I told 3.8 for each cell. So how much voltage it will flow? 3.8 into 3. So here total voltage will be, once we will measure the voltage, if you press voltmeter, one node here, another node here. Okay. So how much this voltmeter will give the reading? This will, because in voltage we have to add the voltage if it is connected in the cell. So 3.8 plus 3.8 plus 3.8, that will be 11.4 volt. Okay, 11.54. So here how much current? 10 ampere and 11.4 volt. You remember that. Okay, for the next battery, there are 4 cells are connected in parallel. So can you tell me how much current will flow and how much voltage will be there? Again, same concept. Voltage will be same in parallel. Okay. So here 3.8, 3.8, 3.8 and 3.8. So total voltage, how much? It will be 3.8 only. Okay. But current, how much? This battery also giving the 10 ampere current. This also 10. So 10 plus 10, 20 ampere. This also 10, 30 ampere. This is also will add. So that will be 10, 30 plus 10, 40 ampere, right? 40 ampere will current will flow. Similarly, here also, how much current it will flow? 10 ampere only, because both are in the series. So 10 ampere here will come. Here also, so 10 ampere plus 10 ampere, 20 ampere, 30 ampere and 40 ampere current will flow. And voltage, how much? 3.8 plus 3.8, how much? 7.6. So 7.6 volt, because again all voltage in parallel, it will be same. So how much voltage we will get? 7.6 and 40 ampere current. Okay. So what will be the capacity of? Okay, we will calculate the capacity of this each type of configuration, because we have to develop the battery bank, right? So for first configuration, how much capacity will be there? Total capacity of the battery bank. And because in first figure you can see there are 3 cells are connected, and if 3 cells connected, that also having the capacity, like energy storage capacity. So how much energy it can store if this 3 cell, forget about this bulb. So how much capacity is like energy is watt into hour, correct? Watt into hour. So how much this current was flowing? Voltage will be 3.8 into 3, that is 11.4. Okay, and current will be same. So 10 ampere into hour. So how much energy we can store it? 11.4 divided by 10 into 10. So 114 watt hour. 114 watt hour, 114 watt hour. Means we can take 114 watt for 1 hour. For 1 hour. If you are taking 20 watt bulb, okay, how much bulb? 20 watt bulb. So for how many hours you can, this battery bank can sustain the current? So you can, if around 100, it is 114 watt, but if you will take 100 watt hour, divide 20. So it can deliver the it can be glow till 5 hours, right? So in such way, we have to develop the battery bank. So if there are so many series and parallel configuration is there in the battery bank, we can reach to the 40 kilowatt and hour. Like here, how much it was? 114 watt hour. That is watt hour. Kilo means more cells should be there. So this is series and parallel configuration, and that we require to develop the battery bank. So if you have any doubt on this, you can ask. Okay, then we will move for next things. So when we were discussing about the Raycon chart, there we discuss about the various types of the batteries that having the different type of energy density, like energy density versus gravimetric energy density. So again, lithium ion having a different type of cathode material like LCO, NCA, NMC, LMO, lithium iron phosphate, and LTO. Okay, so comparing to all types of the batteries or all type of the cathode properties, I have taken this from one MDPI journal. So comparing to all types of the cathode materials, we can see this NMC and lithium iron phosphate batteries are more used in the EV sectors for developing the battery bank. Okay, because it having the high specific energy capacity and safety, specific power, lifespan is also more, and performance is also more. Okay, so if you are developing the battery and before making it commercialized, we have to test the battery. So there are different types of tests are available in the current scenario. So I have taken this from the USABC protocol, that is a United States Advanced Battery Consortium. From there, I have taken this test procedure. So generally, battery test is divided in 3 parts. That is performance test, safety and abuse test, and life cycle test. Performance test having the constant current, variable power test, drive cycle. Then life cycle having the accelerated aging and base life cycle test. Variable power test is FUDS, that Federal Urban Drive Schedule Test. Hybrid pulse power characterization test, dynamic state test, and this is drive cycle. Which one? This NEDC, UDDS, EPA, that is Environmental Protection Agency, is there, that developed the US06 drive cycle that will run for the 600 seconds. Okay, and IDC, that is Indian drive cycle. Still, there is no standard for the Indian drive cycle, but I mentioned here. So there are different drive cycles. We have to, like, if you have the battery, we have the EV there, a battery bank is there. So when you are traveling with the battery, means that car, and some hilly area came, okay, so your driving behavior will change, okay, based on the area condition. If it is plain area, then we can travel easily. But if it is hilly area, so you have to extract more current. Then again, if slope came, then you have to stop taking current from the battery. So it will change as per the driving behavior, right? So so we have to test the battery with different types of test conditions or circumstances. So here, this is the US060 UDDS, NDC, and FTP. That is the drive cycles I have taken here. This I have generated through the one drive cycle. Once you will open the MATLAB, there you can generate this type of graph, and you can keep in your research paper, because this I have not taken anywhere. I only generated through the MATLAB software. You can also generate similarly, when you can keep in your research paper. So there are different type of drive cycles is there. Okay, NEDC, UDDS, DST, Beijing Dynamic Status, Indian drive cycles. So what will be the, if you kept your battery in the EV, then what will be its performance based on the road condition, right? So we have to test the battery. Okay, next, this is CCCV charging. This is what CCCV charging means. What is the meaning of CCCV charging? That is constant current and constant voltage method. Okay, this here I need your attention. This is very important concept in the battery. Okay, so yes, I told, if you are aware, if you are active in this session, definitely it will be helpful. It's going to be helpful for you. So every type of charging station, they are using the CCCV protocol. Okay, so that is constant current and constant voltage. So as I told when I started the session, like either we can take the current from the battery, or we can, that is, if we are taking means we are discharging. If you are giving charging the current means we are giving the current to battery. Okay, that is charging condition. Okay, so we have to charge and discharge the battery, but which component will vary? That is voltage. That is voltage. Voltage will be affected because of our charging and discharging pattern. Okay, so when we are charging the battery, we have to apply the CCCV protocol. So when we will charge our cell, okay, when we are charging, this is a 20% charge was there, and this is 100% charge. Okay, so when we were charging, you know, our this is the current. When we were charging, our voltage also will increase. Voltage also will increase. Like battery having the peak voltage, cut-in voltage, and cut-off voltage. So I taken one example, that is 3.8 volt. That was the nominal voltage of the lithium-ion cell, and it may reach to 4.2 volt maximum. If okay, and it may go it will not go below 2.5 volt for the lithium-ion. Okay, so that this is the nominal, this is the peak voltage, that is cut-off voltage, and this is cut-in voltage. Right. So if we are charging our battery, okay, and you charged like 100% came, yeah, 100% SOC came, right? Again, if you charge with the same current charging rate, you know what will happen? Your voltage will increase. If your voltage will increase, means your battery will be blasted. Okay. So how to avoid that blast condition? How to avoid that blast condition? EV. So we need to follow the CCCV charging protocol. Okay. So I mention here one diagram is there. I will explain this. This is the graph for CCCV charging. Okay. So you can see here, I have in the time axis, you can see 10,000 cycles, 10,000 seconds, 10,000 second, 10,000 second. This is the results of one single simulation result, because you can see the time, times is same in all conditions. So what we are doing, like firstly we were applying the constant current. So this is the 15 ampere. We are charging the 15 ampere. So when battery was discharged, you know how much voltage was there? 3.8 volt was there. So when we started charging with constant current, our voltage also started increasing, right? But it was constant current. You can see this is constant only now. So constant current, and we came here. Okay. That time, you know, our voltage reached to its maximum capacity. Okay, like 4.1 volt. So again, if you will charge, if you will keep our constant voltage current, you know what will happen? Our voltage will start increase. Okay, will start increase. Right. So here you just try to match both. This is the current we are giving to the battery. This is the voltage that is affecting, that is changing as per the charging current. This is charging current, right? So we were charging constant current. So with constant current, we reached here. But again, if we'll give continuous constant current, our voltage will rise. But we don't want to it rise. If it will rise, blast will happen. Means battery may be blasted. So that time what it reached to 4.1 volt. So that time we need to decrease our charging current. Okay, we need to our decreasing gradually. We have to decrease. So once we will gradually decrease, our voltage become constant. So this will be the CV condition, and this is CC condition, constant current and constant voltage. Okay, here in first condition, current was constant, but voltage was not constant. Okay, in second condition, like we have to shift to CV method, that is constant voltage. So we have to maintain our constant voltage. That time, how we can maintain? Through gradually decreasing the charging current, right? So blast will not happen, right? And you can see here, this year like 90% came, so that was 4.1 volt. So we don't want to increase this 4.1 volt when during this 90% or 85% charging, right? So we shifted to CV protocol, that is constant voltage. So it was constant. You can see here constant voltage only, right? This is constant voltage, and we decrease. So this is CCCV protocol, and you can see in this combined graph. First one blue color is battery current, right? This is combined graph, but this is my simulation result that I have kept here. This is my simulation result, but through this graph also we can understand. So when we were giving the, we are charging the battery with some constant current, that is blue line is constant current. That time you can see voltage was increasing. So voltage came to this 4.1. Okay. So again we will give if constant current, again it will increase, but we don't want to increase. We want to decrease. We want to keep constant, because our maximum cutoff voltage was 4.2 volt, right? If it should not be more than this. So voltage will be affected because of this current behavior. So we want to keep the constant voltage. That's why we shifted to CV mode. So this is CV mode. This is CC mode. I hope everyone understand this CCCV. Then battery capacity. Okay. So if any doubt is there in CCCV charging, definitely I am there to solve that. Okay. Next one is battery capacity. How to understand the battery capacity? So an automobile battery might have the 200 Ah capacity. How long this battery can supply 20 ampere? So you try to remember one formula. In upcoming slide also we will use. So if you want to calculate the time, so always you remember time will be capacity divided by load current. Capacity divided by load current. Okay. Capacity divided by load current. How much capacity is there? 200 ampere into hour. And how much is the battery supply? That is load current, that is 20 ampere. So we can calculate 10 hour, means we can take the 20 ampere current from this battery bank for 10 hour. Okay, that is battery capacity. So you remember capacity divided by load current. Okay, now we will move for the C rate. So if you have purchased one battery, like you have one mobile, there 5000 mAh capacity is there. How 5000 mAh, that is milliampere hour. Okay, so if you want to convert in the AH, we have to divide by 1000. Means what? This battery can deliver the 5 ampere current for 1 hour. Okay, that is 1 C rate. 1 C rate. 1 C rate. That is defined by the manufacturer. So whatever capacity is there, like 50 Ah, if one mobile battery having the 50 Ah capacity, means what? This 50 Ah means 1 C equals to 50 ampere. Okay, so we will do some calculation. So here I have taken one case, that is we have one battery. What is the capacity of the battery? If my slide is visible to all, capacity of this battery is 12 volt 50 Ah. Okay, so 1 C equals to how much ampere? 50 ampere. Okay. Then 2C equals to how much? Anyone can tell me the answer for this? 2C.
100 amperes.
2 into 1C, that is 50, so 100 ampere. So can you tell me if we are okay, consider this is fully charged battery. This is fully charged and you are taking current. We are discharging with the 2C rate. So how much time it will take to discharge?
30 minutes.
30 minutes, right? Super. 30 minutes it will take because I told one, I given one.
11.
So capacity means time will be, please mute yourself. Time will be capacity divided by load current. Capacity was this, because this will not, this is fixed. This will not increase. We can store only 50 ampere current for 1 hour, right? So you can calculate with various C rate. When you will do some research, it will be helpful. So try to remember capacity divided by load current. So you can see 5C equals to 5 into 50, 250. Now for half C, you give me the answer. If you are discharging this or charging this battery with half C current, so how much time it will take to charge and how much current will be there? How much current it will be? Half C means, this is 1C, half C means 25 ampere, correct? And time will be capacity divided by load current. So time will be increase, right? Capacity kitna? 50 Ah, load current 20. So we can cut, means we can take 20 ampere current for 2 hours, right? That will be the process, right? So now next one is this we have done state of charge. State of charge of the battery. Okay, some for 36 I will complete because there are so many things to discuss. Still we are discussing on some basics. So what do you mean by the SOC? SOC means remaining capacity. Whatever charge is there in the battery, that is SOC. Okay, that is SOC, right? So how to calculate this SOC? Okay, so here I have taken one numerical. There are different methods is there for battery SOC to calculate the battery SOC. Here we will go through one numerical, so we can understand it. Here we will go for the Coulomb counting method. Coulomb counting method to estimate the state of charge. So one battery, we have the 12 volt and 50 Ah capacity. Okay. Okay. Now the load that draws a current, constant current of 10 ampere. This load is there. How much it is required? 10 ampere. So calculate after 3 hours operation or 3 hours of using of this bulb, how much SOC will be there? How much SOC will be there? How to calculate? So what is the capacity? Capacity was 50 ampere hour. Okay, means it was fixed. Okay, now how much we are taking? 20 ampere. So 20 ampere we are taking for how many hours? 3 hours. Correct. 10 ampere. Here you can see this 10 ampere we have utilized for 3 hours. So 10 into 3 hours. So how much AH we used? 30 AH used. Okay, 30 AH. So how much SOC we used? Means 30 AH already we have used, and how much total was there? 50 AH. Okay, so how much capacity we used? We can calculate. Means to 60% SOC we used. If we use the 60% SOC, then how much is remaining? Means 40% charge is there. Okay, 40% charge is there. That was simple method. But again, through the Coulomb counting, we will understand it through the Coulomb counting. So SOC used, Coulomb used, and total Coulomb. So how to find out this total Coulomb? Okay, so we need to calculate firstly total Coulomb, then we can calculate how much Coulomb is used, then we can calculate the Coulomb used, then we can find out the SOC. So this battery capacity is the 50 AH. 50 A, H means hour, 15 ampere hour. Okay, this is current. So what is the formula for the current? Formula for the current is ampere means Q by T, Q by T into hour. Okay, so 50 into Q is coulomb. Okay, that is you can see coulomb, and C time is second. Okay, and hour means how many seconds will be there? 3600 second. Okay, so you can cut and you can calculate the total coulombs. So total coulombs, how much it will be? 50 into 3600, that will be 1,80,000 coulombs. How much coulombs is there in this battery? 1,80,000. Now how much we used? We used 30 Ah. Okay, 3 into 10, 3 hours. You can see 3 hours into 10, 30, it will be 30 A into H, right? So how much coulombs we use? 30 into 3600 coulombs, that will be, once we will calculate, 10800. Okay, 18. Okay, this we have used. Okay, now again you put this value 108,000 divided by 1,80,000. So how much it will be? 108 divided by 180 into 100. How much SOC we used? So we can calculate. I am calculating through this. 108 divided by 180 means 60% we use. And previous formula also we calculated same. 60% SOC we used. So if 60% we use, initially it was 100% minus how much we use? 60. So how much SOC will be there after 3 hours use? 40% SOC will be there. Okay, so you can calculate the SOC with this method. This is easy only. Okay, here some is there. Then, like if you are traveling from Bengaluru to Mysore, okay. So you are traveling with EV, right? Okay, so initially it was 100% charge. So when you came in middle, you saw somewhere charging station. That time when you saw your battery bank, so it was showing like 50% charge only which available. 50%. Earlier it was 100%. So what you will do? You will charge this battery bank, right? But again you don't have time. So you want to reach somehow this 50% to 80%. Okay, so how much time it will take to charge? So this is the formula. Your capacity was 200 Ah. Okay, and how much? 80%, 30% you want to increase now. 80 minus 50 into with how much is charging rate? 20 ampere. So you can calculate the total hours, how much charging time it will take. Okay, so now we'll come to the our main thing, like how to estimate the parameters and what type of parameter. So there are different type of models are available for battery modeling: empirical modeling, electrochemical, and data driven and electrical event. So when I told in starting, terminal voltage will be the function of open circuit voltage, SOC, I, that is current, RC component, and temperature, right? So easily we can deal with these parameters, and this is highly understood and widely used in the SOC estimator and having the high accuracy. But problem is the complex parameter identification, like how to estimate the parameter. So like this, you will see this is our electrical equivalent circuit model, right? This is equivalent. So this is RC branch, this is R, this is C, okay, and this is internal resistance. So this is R is the function of SOC and function of temperature. This SOC also is the function of SOC, that means charge versus temperature. Like how we can understand it? Like this is car is there. This is your car, okay, and you are traveling in the Rajasthan. There are 45 temperature was there. So and this battery bank was developed based on the electrical equivalent circuit model. So what 45%? 45 degree temperature was there. 45 degree temperature. So what will be the R value and what will be the C1 value? Okay, What will be the R naught value? Because your battery should behavior under wide variety of conditions. Wide, it may be the Arctic zone or it may be desert zone. So what I did, I have estimated the parameters for different types of electrical equivalent circuit model. I have developed the one RC to 5 RC equivalent circuit model, and I have validated that. Okay, so what I did first, like I have taken one 18650R. So what is that? 18650. 18 is the dimension, 18 mm, and 65 mm. Okay, that is a dimension, means this is length and this is width, right? This is 18 mm, this side is 65 mm. Okay, so I have taken one NMC cell. I kept inside one environmental chamber. So this space, when during my PhD in the MNIT Jaipur, we created one environmental chamber that can create the environmental condition like Arctic to desert. Okay, so here we created 0-degree temperature, and we also created 45-degree temperature, and it was varying based on that weather condition. Okay, so what we did, we given some environmental data like for particular day, like how much it was increasing. Okay, like 0, 25, it may be so many temperature, because temperature is varying, right? So we have created that facility, and we kept inside this battery bank, and we taken the battery parameters, like we taken the voltage, and we taken the current, charging and discharging current. Okay, so we taken the experimental data from this battery bank, and I developed one RC equivalent circuit model. This is one RC equivalent circuit model, you can see, and I estimated that parameter, because if temperature is 25 and SOC like temperature is 25, and in your car 40% charge is there, that time what will be the your R1 value or R2 value and R3 value, whatever. This is 2 RC equivalent circuit model. So what will be the your how to estimate this parameter? Like this. There are 11 cross 3 parameter. That 11 is the SOC breakpoint. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is the SOC breakpoint, and 3 is the temperature breakpoint. So there I taken 0-degree temperature, 25-degree temperature, and 45-degree temperature. So I created this that condition, and I created an incremental OCV test profile, because I want to estimate the parameters. Okay, so this is my equivalent circuit model, and I estimated the parameters for these values. So this is a equivalent circuit model estimation model. Okay, inside this I have kept this 1 RC to 5 RC. So how it will look like this inside this, once you control U, once you press CTRL plus U, you will get this type of equivalent circuit model inside this. Okay, so I given the original, means real profile to this battery model, and I estimated the parameters for R1 and C1 and VT and R naught, that is for 1 RC parameter I have estimated. So there are several iteration it taken. Okay, so I will show you that algorithm, like what algorithm I used here. Okay, this is the algorithm. So first of all, as I told, I taken one I conducted one OCV test profile using that environmental chamber with 0-degree temperature, 25 and 45. Okay, then I developed one battery model in the MATLAB. This is MATLAB model, that is 1 RC equivalent, and I define the basic battery physical properties, like what is the length, what is that width, and what type of heat convection is that. I have defined all types of the battery properties, then applied this non-linear least square algorithm and estimated the parameters. Okay, so here initially, like here you can see both simulation and experimental, both. This is OCV profile, incremental OCV profile. So this is simulation Blake. So when I started simulation, it was constant, like I have given 3.8 volt. So with various iteration, it merged, like red is experimental, so red will not change. What parameters will graph, which graph will change? This simulated, means this Blake simulation graph will change. Are they in starting condition? It was 3.8. Okay, so with several condition, it will merge, both graph will merge. Okay, so once it will converge properly, when it will, you can see in this graph, it merged, means it will merge means we are able to estimate the parameters. So when it will converge, we will get the parameter, estimated parameters for the battery. Okay, this is little bit typical, but we need, because again we have the battery ECM cell, there we have to put these values. Okay, so here you can see, as I told, this is measured. Okay, and this is simulated, red is simulated. So here 3.8. Okay, and this is our measured. So once with several iteration, okay, so we need to estimate the parameters. So this work, and you can see I have tested this hardware results and simulation result, and I have compared. So my battery model was battery model behavior was very accurate, and I was able to compare the experimental data and simulation data. So both graph is matching properly, and I got the very minimum error, means in the simulation and the hardware. Okay, so these are the my results, and I here for checking the behavior of my battery model, I taken the this 4 different type of drive cycle: FUDS, Federal Urban Drive Schedule, DST, BJDS, and US06. Okay, this data is available in one website is there called Center for Advanced Life Cycle Engineering. That is, I have taken prior permission from University of Maryland, and they provided this data, and I matched my battery model with this. So this was older technique, okay, for developing the battery model. But nowadays, this network people, they are very advanced, and you can't even modify any equivalent circuit model. Okay, that time I have modified, and I extended 1 RC equivalent circuit model to 5 RC equivalent circuit model, and I have estimated the parameters for everything, right? But nowadays they have the one battery builder. Okay, so what you can create the cell first. You can create the cell, there you can define the whether this is 1 RC or 2 RC. Okay, there in MATLAB, and you can create the cell. This is cell, then this is parallel assembly. So once we will connect this parallel assembly, we can create the one module, right? So this is the module. This is parallel assembly. This is the smallest unit, that is cell. Then through the module assembly, we will create the one module assembly. And in battery pack, there will be so many module assembly will be connected. Okay. So what you do, you can open this battery builder in your MATLAB. So once we will type this battery builder also, like you just type this in your command window, you will get this type of screen. So there you can select. First of all, you should select this cell. Okay. Then you have to define the parameters. Like you take one original cell parameters and you define there. Like what is that radius, height, position, right? So you can create one cell. Okay. Then there I have taken one example. I am not opening the MATLAB because of this time constraint. I will finish within 5 minutes. So you can create the cell and you can define their properties of that cell. So what you will do, how to create this cell? You click on this cell, right? Then you can create whether it is cylindrical, pouch, or prismatic, right? And you click on new cell, not example cell. You have to click on new cell, means you have to give the name as a new cell. Any name you can give. You can give like Panasonic or a Samsung, any battery name you can give. Okay, so this is the process to develop the cell. Then these are the parameters you can apply. Okay, so here I have selected one pouch cell. So because of that, this type of cell is appearing. Okay, once your cell will be done, same cell properties will be used for the parallel assembly. So once you will complete this, you have to go for the parallel assembly. Okay, so for the parallel assembly also you have to select how many cells you want to connect in the series and parallel configuration. So you can select in the you can create one parallel assembly. So here I have taken three cells, and I connected and I created one new parallel assembly. Then with the help of parallel assembly, you can create the module. So click on this module and select your previous parallel assembly you created. Okay, again this parallel assembly, when you will create this parallel assembly, previous cell that you created, that you have to select, not example cell. Okay, that is an concern here. So you create the module based on the new parallel assembly. Okay, so once module will be created, and there you have to do the properties like how many assemblies you want to connect in the series and parallel, and how much gap you want to keep between. Why this gap? Because flow of air should be there, you know. So you can that means you can maintain the temperature, right? So with the help of this module, you can create the module assembly. So we have done this cell, we have created parallel assembly, we have created module. Then click on the module assembly based on the module that what you have created previously, right? So you have to select that module and you have to click on plus 4-5 times, that how many modules you want in your module assembly. You can click plus. After selecting, you click on plus. So here new cell, new model will appear, right? So you can create the module assembly. After I have selected two module assembly. Sorry, here two module 1 and module 2. So that's why 2 module is appearing here, right? And this is pouch cell. Then you finally you can go for the pack level. So here you have to select previous new module assembly that what you created previously. Here 5 pair 1 2 3 4 5 module assembly I have selected. So in my battery bank, how many module assembly will be there? 5, right? So once and you have to define pooling, and there will be n number of so many parameters that you have to take care. You have to take the original data and you have to feed there. So I have created one battery bank that having so many module assembly 1 2 3 4 5 and two parallel. Okay, so you can create, and you may also get the certificate from the MATLAB. So once you will do free of cost. Okay, so within 3 minutes I will tell that like what you have to do. My screen is visible. You just type MATLAB here. And you log in with your credential. If you having the MATLAB credentials, if your campus wide license you will be having. Okay, there will be a number of courses. So you can sign in. I have already MATLAB account, so I will sign with my credential. So free of cost you may get this license, certificate in battery bank. Okay, so here I'm just telling that process. You click on this your account, right? Go to my account, and there will be so many courses. So you select this battery battery builder, means this I will show you. You can see my screen here. You can see my courses, right? And in my courses there will be 92. Earlier it was 82. Now they increased. So you can see I have completed some courses completed. So this is Simscape battery one type. So here you can see the certificate. You click on this, you will get that process. Whatever I have mentioned, same thing will be there. Okay. You should try to get. So you here you can see the certificate. Okay. It will be helpful for you. Now you can see my certificate here. So with this, I want to end up my session here. Okay. Like this, you can complete your, if you facing any problem, you can approach me. So once you can connect me through the link, LinkedIn. There I am always active. Definitely I will help you. Okay. So I want to thanks to sir for inviting me to deliver the session. So here I am requesting to participant, if you have any questions, you may ask.
Thank you, sir. Sir, actually,
Welcome,
it is
sir.
very
So
interesting.
if any
So, due to time constraint only, we are requested actually, if you don't mind, because next session we have to start at 5 o'clock. From the participant side,
okay, sir.
any question? Sure. Now we are move on to validity. It's my privilege and honor to deliver the vote of thanks for this enlightening FDP program on modeling of lithium-ion battery for EV vehicle and application. I would like to extend our heartfelt gratitude to our speaker, B.L. Bhairava, Dr. B.L. Bhairava, for their inspiring and thought-provoking sessions. Your expertise and insights have provided us with a deep understanding of battery technology and EV vehicles. It plays in shaping a sustainable future. To our participants, your active engagements have been remarkable throughout the program. Your insightful questions and discussions have truly made this FDP dynamic and meaningful. Once again, thank you all for your presence, participation, and contribution. Let us continue to work together toward a greener and more sustainable future. Thank you, one and all.
Thank you, sir.
Okay, sir. Thank you, sir. Now, all the participants, just to log out from this session and join on the next session. Please, thank you. Thank you for your support. Please, leave the session now. Thank you, one and all. Sir, Bhairava, sir, very much thankful, sir.